Good afternoon, one and all. Welcome to 122nd episode of Creative Online Talks. I am Supriya, your host for this enlightened discussion on the gravitational and optical wonders of Newtonian physics. This talk is not just a convergence of ideas, it's a tribute, a heartfelt homage to the late Professor G. Venkatesh, a luminary who dedicated his life to science communication. Creative. The force behind this intellectual gathering is more than just a group. It's a community of like minded individuals driven by curiosity and a passion for acquiring new knowledge. The name itself, Creative, embodies the essence of our mission. To be active, we need to be creative. In this dynamic space, we believe that a fusion of creativity and activity leads to a deeper understanding of the world around us. With knowledge square as our guiding principle, we strive to amplify our collective wisdom by focusing a cultivate a culture of sharing. Our vision at Creative is to cultivate constructive thinking across various domains. The main focus on non-textual, non-academic, non-syllabus concepts that broaden our intellectual horizon. Every Saturday, we come together on the virtual stage of Zoom, and our discussions are beamed live to our YouTube channel, Creative GBD. Through this online weekend talks, we aim to ignite intellectual sparks, encouraging everyone to join us in this continuous journey of discovery. Thank you for being the part of Creative Online Weekend Talks, where knowledge knows no bounds. I welcome today's speaker, Dr. B.S. Srikanta sir, for accepting our invitation and for gathering here. And I welcome all the participants of today's session, and I call Srinath sir to introduce today's speaker. Over to Srinath sir.
Good evening, good afternoon, and namaste to all. First of all, special tribute to Professor G. Venkatesh, who is the guiding spirit for the creative team as well. Today's speaker, Professor B.S. Srikanta, who is the best suited person and as well as the co-worker or colleague of Professor G.V. That's the reason today we have Professor G.V. Memorial Talk. It is my special privilege to introduce Professor Srikanta. For those who are associated with Gauri Bidur National College, he is a popular physics teacher. Before moving to Bangalore for his career excellence till 1976, he worked in Gauri Bidur National College as a lecturer. Later, he became a principal in RBNMS First Grade College. More than 27 years, he has worked there till his retirement. Coming to his academic credentials, he holds BSc and MSc Physics from Bangalore University. He also has a PhD from Raman Research Institute under the guidance of Professor N.V. Madhusudana. He has an impressive record for more than 47 years of teaching, as well as the administration in the colleges, especially science colleges. As an institution builder, he played a pivotal role in transforming RBNMS College, fulfilling the founder's vision of empowering through education. Dr. Srikanta is a prolific researcher with more than 16 published papers in the national and international journals. He has authored 8 textbooks, one book along with Professor GV as well, whom we are dedicating today's talk. And he has actively encouraged scientific zeal among the students. His commitment extends beyond the academia. He has served on various Bangalore University bodies as well, contributing to 27 committees. His impact is even evident in his role as the president of the Bangalore University First Grade College Principals Association for nearly a decade, and is an extensive service in the first grade degree college Principals Association in Karnataka. He is also the founder member and executive member of the Karnataka Physics Association. Presently, he serves as a member and member coordinator for NAAC NAC peer team, demonstrating his commitment to the quality education. Dr. Srikanta's contributions have been recognized through awards like Lifetime Achievement Award, Rashtriya Shikshana Ratna Award, and Seva Ratna Award, among others. A well-traveled academic, Dr. B. Shrikant has visited universities in the USA, Germany, France, UAE, and Italy. He remains highly regarded for his commitment to the teaching in institution building, effective administration, and his contribution as a compassionate human being. Moreover, currently he is guiding a lot of Karnataka Physics Association, and I am being part of KPI. I had the privilege of working with him, and I am very happy to see him in many occasions during the meetings. And today, to commemorate or to honor or to respect our Professor GV, who was the founder president of KPA, I take the privilege and also join with Supriya to welcome today's speaker. Sir, thank you for accepting, sir, and pleasure listening to you. Now over to Supriya.
Thank you, Srinath sir. Over to you, sir.
Namaste. Namaste.
You can start, sir.
Maybe one last dialogue. There are so many people who are students of Srikanta or the National College people or KPA. I take this opportunity to extend welcome to all the dignitary participants. I cannot take time reading each and everyone. I request all, I extend my welcome to all. Over to Srikanta, sir.
ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರ. I hope I am audible.
Yes, sir.
ಕೇಳಿಸ್ತಾ ಇದೆ ಅಲ್ಲ?
Yes, sir. Yes, sir.
ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರ. Very good afternoon to one and all present. I am today speaking with immense grief and sadness in my heart to pay tribute to a very kind soul, disciplined mind, a good friend, mentor, and a dedicated teacher of physics, Dr. G. Venkatesh. Frankly speaking, we are not happy to participate in this program because we should not have got this opportunity to organize a function of this type. But anyway, of course, nobody can avoid death, and it is not in our hands. And it was really when we heard the news about the sad demise of Dr. G. Venkatesh, it was indeed a shock to all of us. And as we know, that death is in not our hands. And we are paying tribute to Dr. J. Venkatesh, who, according to me, drank, ate, and breathed physics throughout his teaching and administrative career, spanning over 5 decades. When I make this statement, I have a reason. When he was admitted to the hospital for bypass surgery, he attended online lecture from the hospital, lying on bed. My association with him started way back in 1976, as Mr. Srinath mentioned, when I joined AES National College, Gauribidnur, as lecturer in physics. He was my head of the department. It's indeed a very long association of 47 years. Even today, I am not able to digest the fact that he is not in our midst. Personally, it is a great loss to me, as he was my mentor, guide, and a good friend. Dr. G. Venkatesh most unexpectedly left for his heavenly abode on 8th November 2023, leaving behind his wife, 3 sons, daughters-in-law, grandchildren, and a host of relatives, friends, students, and admirers. His sudden death has put his family members, students, friends, admirers, and associates in a deep sense of sorrow and pain. When we heard about his death, as I told earlier, it was indeed a great shock, and still we have not come out of that shock. Dr. G. Venkatesh was born on 18th October 1945 as the second child to his parents, Sri Gundupatta and Srimati Kamalama. Dr. Venkatesh had his early education at Gauribidnur. He was a brilliant student right from his childhood. He joined National College, Basungudi in 1962, completed his graduation in 1965, securing distinction. He completed his MSc from University of Mysore in 1967, specializing in theoretical physics. In the same year, he joined National College Gauri Bidnor as lecturer in physics and continued to serve the institution till 1992. And during his tenure of 25 years at AES National College, he adorned various positions like lecturer, reader, head of the department, professor, and principal. He was undoubtedly an inspirer to all those associated with physics. He was highly respected and adored by his students for his excellent teaching, scholarship, and deep understanding of concepts in physics. He had earned appreciation from his students for his erudition and sagacity. Many of his students have reached pinnacles in their careers, occupying top positions in several organizations. He had also impressed the managements and his colleagues with his administrative acumen. And during his tenure at National College, he also obtained his PhD from Bangalore University by carrying out research work at Raman Research Institute under the guidance of an internationally known scientist, Dr. S. Chandrasekhar. He was awarded PhD for his thesis titled High Pressure Studies on Liquid Crystals. He had published during several research papers and articles in national and international journals. I feel proud to say that we both have co-authored 4 textbooks in physics for BSc classes. After taking voluntary retirement from National College, he served in various institutions such as Bhagwan Mahavir Jain College, Garden City College, and Indian Academy Degree College as professor and principal for nearly 2 decades. He was appreciated by the managements of all these institutions for his ethical administration and good governance. He was indeed a visionary and a true academic leader who introduced several constructive reforms in the institutions he served. Delving into his academic and co-curricular activities, I would say that it was really mind-boggling. He was involved in a wide spectrum of academic activities. I distinctly remember that when he was in Gauri Bidnor, we started, Karnataka Karnataka Rajya Vignana Parishad, and he was the president of the Karnataka Rajya Vignana Parishad Gauri Bidnor unit. He formed a team of speakers, which included me also, to deliver lectures on scientific topics in high schools in the Taluk. And we used to visit high schools on a weekly basis, carrying all the required paraphernalia with us, like slide projectors and things like that, and used to deliver lectures on scientific topics in order to create interest in science among students. He was very passionate about popularizing science in general and physics in particular among students and teachers. In the later part of the illustrious career, he served as the president of IAPT, that is Indian Association of Physics Teachers Bangalore chapter, and he also served as national level chief coordinator of IAPT examinations. With his meticulous handling, credibility and fairness of the examinations were enhanced by many folds, and the same was appreciated by the office bearers and members of the association. His dream was to start an association at the state level and hence create a platform to propagate and popularize physics and physics education. With his indomitable spirit, he could pull in a team of like-minded people and succeeded in establishing Karnataka Physics Association just a year ago. Many of us joined hands with him in this academic venture, and within a year, the association has witnessed a phenomenal growth, and Dr. GV was instrumental in organizing several programs under the umbrella of Karnataka Physics Association. Dr. G. Venkatesh, popularly known as Dr. GV among his friends, associates, and students, was indeed a man of action, a dedicated, a committed teacher, a scholar in physics, a good orator, an able administrator, a good organizer, a great leader with impeccable character, and a man of higher integrity. Because of his honesty and integrity, he could talk to any person, either his subordinate or higher authority, with courage and conviction. In the untimely death of Dr. G. Venkatesh, we have lost a great inspirer, a mentor, and a good friend. It's difficult to fill the void created by his death. And let's carry forward. Let us dedicate ourselves on this occasion and carry forward the legacy left behind by Dr. G. Venkatesh. On this occasion, on behalf of all of you and also on my own behalf, I express my deepest condolences to the bereaved family and pray God to give adequate strength to bear the loss, which is indeed irreversible, a word that I have taken from thermodynamics, which was dear to Dr. G. Venkatesh. Now, coming to the topic of today's program, Newton, gravitation, and optics. I selected this topic for several reasons. One is, according to me, Newton and Einstein, they stand on the same pedestal. Other than Newton, stands in comparison with Einstein or the other way. Newton, as we all know, called the father of classical mechanics, and Newton ruled the world of physics from almost 1642 to almost 1905, till Einstein came out with his theory of relativity. And also, one thing that I remember is, Newton published his Principia in 1687. And in 1987, Dr. G, under the leadership of Dr. G. Venkatesh, we very meaningfully celebrated 300 years of Newton's Principia. So that's how Newton, was very close to Dr. G. Venkatesh, and we used to conduct, many programs on Newton. And I am also one of the admirers of Newton, and that's why I have chosen this topic, Newton, gravitation, and optics. As you know, Sir Isaac Newton was a brilliant English physicist who lived in the second half of the 17th century and first quarter of the 18th century. He was not only a physicist, but also a mathematician, astronomer, natural philosopher, and of course, an alchemist. And let me make it, let me tell the participants here, he was called a philosopher because during Newton's time, the word scientist was not in science diction. All scientists were called as natural philosophers, and therefore Newton was also called a natural philosopher. The word scientist was coined in 1834 by William Whewell, a Cambridge University historian and a philosopher of science. Newton is best known for his theory about law of gravity and laws of motion. His magnum opus, Principia Mathematica, published in 1687, with a description about the laws of motion and gravity, ushered in a renaissance of enlightenment in Europe in particular and the world in general. And it was actually a culmination of years of research. He established the universal law of motion and gravity, and as I said earlier, he is often referred to as the father of classical mechanics. The second major book, titled Optics by Newton, deals with the properties of light. He also served as the president of the Royal Society of London and Master of England's Royal Mint before his demise in 1726. Coming to in my talk, I'll be I'm dividing my talk into three parts. One is the early life of Newton, and then about his contribution to gravitation and optics, and also the various positions that he held during his life. Isaac Newton was born on Christmas Day. And one more thing is, Newton, was born on 25th December 1642 in a very tiny hamlet of Woolsthorpe, Lincolnshire, England. And it's very interesting to note that in the same year, 1642, Galileo had died on 8th January 1642. Sometimes it is remarked, perhaps, that God did not want to have vacuum in the field of physics and ensured that Newton was born in the same year, and his father was Isaac Newton. Father's name was also Isaac Newton, had died 3 months before Newton was born. His mother was Anna Isakov, and as a very next slide. Yeah. When Newton was 3 years old, his father, died. His mother was Anna Isakov. As a very tiny and weak baby, I'm told that Newton, as a baby was very weak. Everyone thought that Newton would not survive for a long time. Even his first day of life, it is recorded that as a baby, the baby was so tiny that it could be fitted into a big tumbler. But God's will was different. Newton lived for nearly 85 years. Newton's widowed mother married for the second time. She married a well-to-do man, Barnabas Smith, within 2 years of Newton's birth. His mother left young Newton with his maternal grandmother and moved to a neighboring village with her second husband. Thus, Newton was deprived of love and affection of both his parents. It is said that this deprivation of parental affection had a profound psychological influence on Newton. He grew in his grandmother's place for about 9 years until the death of his stepfather in 1653. Newton had his early education in village schools. He studied in King's School, Grantham. In 1659, he was taken back to his hometown. And his mother wanted him to become a farmer. But Newton was very unhappy with this idea. He was very unhappy with the proposal of his mother, and he completely abhorred it. And with the recommendation of his uncle in 1661, he joined a Trinity College at the University of Cambridge at the age of 19 years. When Newton joined the university, the college teachings were based on those of Aristotle. But Newton preferred to read more of advanced ideas and concepts put forth by modern philosophers such as Descartes, astronomers such as Galileo, Copernicus, and Kepler. Newton obtained his degree in 1665, and in the same year, the university was closed for about 18 months as a precaution against the Great Plague. For the next 2 years, Newton worked at his home, Woolsthorpe, on calculus, optics, and law of gravitation. This universal law of gravitation, of course, is very familiar and popular, and I'm quite sure that every high school student knows about the universal law of gravitation. The universal law of gravitation, as enunciated by Newton, states that every body attracts every other body in the universe with a force proportional to the product of their masses and inversely proportional to the square of the distance. It is said that while he was pensively meandering in his family's apple farm, it came to his thought that the power of gravity, which brought apple from a tree to the earth and also made it to fall perpendicularly to the earth's surface, was not limited to a certain distance from the earth. But Newton thought that this power should extend much farther than it was originally thought. The analysis of the circular motion in terms of Newton's laws of motion brought out the point the centripetal force is necessary to divert a body from its rectilinear path. We know from the Newton's first law that when no force is acting on a body, the body continues to move with a constant speed along a straight line. And any deviation from the straight line or any change of speed requires a force. And he thought that for any non-linear, particularly the circular non-linear motion or a circular motion, a centripetal force is necessary. He also found that the centripetal force responsible for holding planets in their elliptical orbits about the sun varies inversely as the square of the planet's distance from the sun. He also argued that the satellites of Jupiter obey Kepler's third law, inverse square law, centripetal force keeps them in their elliptical orbits. In the next slide, I'm just going to show how Newton's deduced or Newton's deduction revealed that a similar relation exists between the Earth and the Moon. Here in the slide, you can see that I've given you the figures. The distance of the Moon from the Earth is 384,401 kilometers, and the radius of the Earth is 6,371. When we take the ratio of the radius of the Moon's orbit to the radius of the Earth, it turns out it is around, the ratio is around 60.33, approximately 60. And very interestingly, the acceleration due to gravity on the Earth's surface, if you take the ratio of the acceleration due to gravity on the Earth's surface to the acceleration due to gravity at the Moon's distance, that is at about 384,401, it turns out to be 3,600, which is square of 60 square. So if you can very easily infer from this that GE by GM, that the ratio of the acceleration due to gravity on the Earth and again to the acceleration due to gravity at the Moon's distance is equal to the square of the ratio of the radius of the Moon's orbit to the radius of the Earth. So you find that the acceleration is inversely proportional to the square of the distance. So acceleration of an object decreases in the inverse proportion to its distance from the center of the orbit. And from Newton's second law, we know that force is equal to mass into acceleration. So gravitational force must also vary inversely as the square of the distance. Since the force, gravitational force must also, so since the force is the product of the mass and acceleration, gravitational force must also vary inversely as the square of the distance. Thus, Newton discovered universal law of gravitation. Newton used Kepler's second and third laws of planetary motion to deduce the theory of gravitation. Here, I would like to give a slight, a brief historical development of this particular concept. As we know, Tycho Brahe, who lived in Denmark between 1546 to 601, he did very elaborate measurements and observations on the planet, on the movement of planets and other celestial objects. He collected huge data about the movement of planets and other celestial objects. But the problem was he could not correlate the data in a proper way. Then Tycho Brahe transferred the data to his assistant Johannes Kepler, who lived between 1571 and to 1630, a German astronomer and a physicist. And Johannes Kepler worked on this data, really for about 22 years. After 22 years of ceaseless work, Kepler succeeded in evolving three laws, which we call today were very famous as Kepler's laws of planetary motion. I'm not going to state the planetary laws of Kepler's laws of planetary motion, because every student of science knows about that. In brief, I tell you, all planets, they revolve around the sun in the elliptical orbits with the sun at one of the foci. And then the aerial velocity is constant. That is the radius vector drawn from the sun to the planet covers equal areas in equal intervals of time so that the areal velocity is constant. And also, the third law says that the square of the period of orbital motion is proportional to the cube of the semi-major axis of the elliptical orbit. But probably Kepler himself would have, come out with the law of gravitation. Unfortunately, Kepler was not aware of the law of inertia. So he could not proceed further. For him, it was necessary to suppose a power acting, he was not aware of the law of inertia. As per the law of inertia, Newton's law of inertia, that any body at rest continues to be at rest, or a body in uniform motion continues to be in uniform motion unless an external force acts on it. And Kepler was not aware of this. And he thought that it was necessary to suppose a power acting continuously on a body in order to move it. But Robert Boyle, Edmund Halley, and others were convinced that a planet could move in an elliptical orbit only if it were attracted by the sun, with a force varying inversely as the square of the distance from the sun. But again, they could not prove mathematically. Then this Edmund Halley, a good friend of Newton and also an admirer and also a good friend of Newton, went all the way to Cambridge to ask Newton if he could furnish the required proof. But Edmund Halley was simply astonished to learn that Newton had already done it years earlier and had somehow lost his papers. And Newton, he also showed that very important thing. He showed that the path of the orbital path of an ellipse under the action of inverse square law. He showed that under the action of a central force, in fact, Newton's argument was a central force which is inversely proportional to the square of the distance. Under the action of such a kind of central force, obviously the orbit of the body should be an ellipse. That was the argument of Newton. Newton showed that if the force decreases as the inverse square of the distance, one could indeed calculate the moon's orbital period and get good agreement. And by 1666, Newton had an early version of his three laws of motion. Of course, he is known for the three Newton's laws of motion, which, of course, again, even a high school student knows about that. Newton showed that the motions of objects on Earth and of celestial bodies are governed by the same set of natural laws by demonstrating the consistency between the Kepler's laws of planetary motion and the theory of gravitation. So, in fact, that's a very important development where, Newton showed that there is a consistency between the Kepler's laws of planetary motion and his theory of gravitation. In 1684, Edmund Halley asked Newton what orbit a body followed under the inverse square force. And Newton immediately replied that it would be an ellipse. However, his notebook, Newton gave the proof of the converse theorem, that if the orbit is an ellipse, the force is inverse square law. And also, most of us in our graduation, our BSc classes, we have deduced the Newton's law of gravitation from Kepler's laws of planetary motion. And one more thing is that how this mass enters into the gravitational force. Because, we always say that the gravitational force F is equal to capital G, which we call it as the gravitational constant, is equal to m1, m2 by d squared. That is, it is proportional to the product of the masses and inversely proportional to the square of the distance. When Newton, introduced this mass concept, and I argued like this, Newton saw that gravitational force between bodies must depend on the masses of the bodies. Since a body of mass m experiencing a force F accelerates at a rate F by m. This follows from the second law of Newton's second law. Since a body of mass m experiencing a force F accelerates at a rate, acceleration is equal to F by m. A force of gravity proportional to m would be consistent with the Galileo's observation that all bodies accelerate under gravity towards Earth at the same rate, a fact that Newton also tested experimentally. You know that important observation of Galileo is a body, when dropped, from a let's say higher level, from an altitude, all bodies, irrespective of their masses, they fall with the same acceleration. That means the acceleration due to gravity is same, irrespective of the mass of the body. That's a Galileo's observation. And Newton said that if I take this mass, a force of gravity as proportional to the mass, this would be consistent with the Galileo's observation, and with that all bodies accelerate towards the same rate. That they are under that, and Newton also tested this argument experimentally. Also, he conducted and he proved this one. And then next slide. Halley's, one more thing is, this Newton was a person with little, was a person of shyness. He was not interested, and also he was not interested in publishing his work or bringing out his work in the form of a book or something like that. That is because of the opposition that he faced from Hooke, actually. When Hooke was the president of the Royal Society, I think there was some sort of, not a good understanding between Hooke and Newton. So he was a bit hesitant to publish his work. But Edmund Halley, motivated Newton to write the full treatment of his new physics and its application to astronomy. For a year, in 1687, Newton's Principia was published with the financial assistance from Halley. It consisted of Newton's laws of motion and the law of gravitation. And Halley used Newton's method and found almost a parabolic for the number of comets. That's another important thing. Halley, made observations about the comets when he computed the orbits for 3 comets, which were observed in 1537, 1607, 1682. He found that they were the same comet. It is the same comet that appeared again in 1456 and again in 1378. He predicted that the comet would appear in 1759, and it did appear in 1759. And as we all know, in fact, I have also observed that this comet appeared again in 1986, and now it is expected to appear again in 2061. And this comet, again, it's based on, he worked out on the basis of Newton's law of gravitation, and this comet is very popular as Halley's comet. Then, digressing a little from the topic, I would like to, I try to learn about, tell you about what were the impediments for the new theory of gravitation. What were the impediments faced by Newton to propose his theory of gravitation? The main hurdle for the development of the new theory was Aristotle's argument and Descartes' vortex theory of gravitation. Aristotle's arguments were like this. A stone falls because it has the nature within it. The natural motion of heavenly bodies is circular. That means, he always thought that, even Copernicus for that matter, he thought that, they go around the circular orbits. Only Kepler, later on, even Copernicus also, though he, advocated the heliocentric solar system, heliocentric system, but he still believed that the planets revolve around the orbit around the sun in circular orbits. But later on, it was modified by Kepler with elliptical orbits and all that. The natural motion of the heavenly bodies is circular. An object moving at constant speed requires a continuous force acting on it to maintain speed. But now we know, as per Newton's first law, force is not required for a body to move at constant speed. And of course, along a straight line. And he also, Aristotle said, that force can only be applied to an object through contact. But whereas in the gravitational force, it acts at a distance. Here, in the case of gravitation, it is a force acting at a distance and not through contact. And even Aristotle also said, contrary to what Galileo said, heavier objects fell more rapidly than lighter ones. According to Descartes, vacuum could not exist in the universe. It's filled with ethereal matter consisting of eddies, vortices, and whirlpools. And these were the, causes, these were the impediments for the new theory of gravitation. Another, now, of course, now you know that to test the theory of gravitation, Newton wrote to Flamsteed, another astronomer and a good friend of Newton, to ask if Saturn had been observed to slow down upon passing Jupiter. The surprised Flamsteed replied that the effect had been indeed observed. And you know very well, Newton, in mechanics, Newton enunciated the principles of conservation of momentum and also conservation of angular momentum. He also formulated an empirical law of cooling. In fact, it is famous as Newton's law of cooling, which states that the rate of cooling is directly proportional to the temperature difference between the body and the between the two bodies, or between the body and the atmosphere. And he also studied the speed of sound in gases, and he even derived a formula for the velocity of sound in gases. And we know that V is equal to root of P by rho, that is only pressure divided by density. But later on, of course, it was corrected by Laplace, because Newton, in his derivation, or when he derived the expression for the speed of sound, he assumed that the isothermal conditions prevail in the medium. But later on, it was argued by Laplace that adiabatic conditions exist in the medium, and therefore it has to be corrected. And today we have a Newton-Laplace equation, which says that V is equal to root of gamma P by rho, where gamma is the ratio of the specific heats of the gas. Next, of course, with this, though I don't, you know that in 1905, Einstein proposed his theory of relativity, and with this theory of relativity and general theory of relativity formulated by Einstein in 1905, of course, the concept of gravitation has changed now. You know it very well. And also, according to Albert Einstein's special theory of relativity, the maximum speed of light, the maximum speed that we can attain is the speed of light. The principles of Newton's mechanics fail when we approach the speed of light. Newton's law of gravitation has an inherent assumption of action at a distance. But according to this assumption, displacement of one mass is instantaneously communicated to other masses. Einstein argued that signals cannot be sent at a speed faster than the speed of light, and Newton's theory had no answer for this. And according to general theory of relativity, you know that gravitation is not a force between two objects, but it is the result of an object responding to the effect of the other in the space-time surrounding the object. And according to general relativity, gravity produces curvature in the space around a massive body, and the general theory of relativity challenges this aspect. It says only empty space, as empty space is flat, the presence of mass covers the space around it, and the motion of any other mass is just a response to the curved space-time. So I think with this, I discuss about, I think this is enough for the gravitation as far as the gravitation is concerned. And now I shift to the Newton's work on optics. In fact, when Newton's first work as a Lucasian professor was on optics, in 1666, Newton observed that a prism refracts different colors by different angles. This fact made Newton to conclude that color is a property intrinsic to light. Newton investigated the refraction of light and demonstrated that white light passing through a prism splits into constituent colors, producing a multicolored image, which he called it as spectrum. He also showed that the colors could be recomposed into white light by using a lens and a second prism. He discovered that white light consists of 7 colors, namely Vibgaya. And one more important discovery or observation by Newton is that the color is the consequence of objects interacting with the colored light, but not the objects producing color themselves. See, that's a very important, he said. He said that the color is a consequence of the objects interacting with the colored light and not the objects producing colors themselves. And this is called Newton's theory of color. Newton concluded that any lens used in a refracting telescope suffers from the defect of chromatic aberration. This made him to construct first reflecting telescope, and in fact, he used Newton's rings, which is very familiar to all physics teachers, to test the quality of optics. And because of this invention of reflecting telescope, he was made a fellow of the Royal Society of London. It is worth mentioning here that earlier to Newton's work, every scientist, including Aristotle, had believed that white light was a single entity. And Newton also proposed that, Newton is also, that he discovered the dispersion of light. Of course, dispersion is essentially due to refraction, and which again depends on the refractive index. And refractive index is different of a material, is different for different colors, and that leads to dispersion of light. Another important contribution of Newton, of course, today we have discarded the theory, is Newton proposed his corpuscular theory of light. He argued that light composed of particles or corpuscles are not to be mistaken for the present photons. The present particles, what we call as photons. And these corpuscles were refracted by accelerating towards a denser medium. These particles are so tiny that they can travel through the interstices of the particles of matter with the velocity of light. When these particles fall on the retina of the eye, they produce sensation of vision. Though the theory could account for the optical phenomena like rectilinear propagation of light, it could not account for simultaneous reflection and refraction. And also, according to his theory, according to Newton's corpuscular theory, light travels faster in a denser medium than in a rarer medium, which is contrary to the observation. We know that light travels, faster in a rarer medium than in a denser medium. And in this, that Huygens proposed. In fact, I want to add a few more points here, particularly what happened and how this. There was a fight between the advocates of Newton's corpuscular theory and also the Huygens wave theory. Christian Huygens proposed the wave theory of light. And wave theory of light could account for, Newton's corpuscular theory failed to account for interference, diffraction, and polarization and things like that. But Huygens wave theory could explain the interference, diffraction, and polarization, the Huygens wave theory of light. And some people, of course, advocated the corpuscular theory because Newton was at that time a very powerful person, a scientist. So there were people, who believed in Newton's corpuscular theory, and some of them, they believed in the Huygens wave theory. In 1807, Thomas Young demonstrated this interference phenomena with his double slit experiment in 1807. And 10 years later, Fresnel, who was actually an engineer, not a physicist, he came out with the theory of diffraction. Diffraction is what is a bending of light around the corners of objects. Fresnel came out with the theory of diffraction, and the scientists, of those at that time, they wanted to resolve this issue because there were like two groups of scientists, one supporting the corpuscular theory and other supporting the wave theory. And the president of the French Academy of Sciences, Professor Arago, was the president at the time. He wanted to solve this problem, and he held a competition. like, people can come out with a theory, either supporting the corpuscular theory or the wave theory. Fresnel came out with a theory supporting the wave theory of light. And according to Fresnel's theory, a very important observation, one has to please note that when you keep a circular object in the path of light, we generally expect the shadow. We expect a dark shadow. That's a natural, common sense. That's what we observe. But Fresnel's theory, according to Fresnel's theory, if I keep a circular object in the path of the light beam, the Fresnel's theory predicted a bright spot at the center of the shadow. A bright spot at the center of the shadow, which is difficult to understand for a common man. Then, one of the committee members named Poisson, we have heard of Poisson. Poisson was an advocate of corpuscular theory. He ridiculed the argument of Fresnel, and he said it's ridiculous. It was ridiculous. He did not, agree with the Fresnel's theory. But the president of Arago, who was a very impartial, he himself conducted the experiment. He himself conducted the experiment with this, keeping a circular disc, in the path of the light beam. And he did, when he conducted the experiment, he did observe a bright spot at the center of the circular shadow, thus giving credence or credibility to the wave theory of light. And this was a deciding experiment. And this decided the fate of the wave theory and also the Newton's corpuscular theory. And with this, the Newton's corpuscular theory was given a death blow. And in this slide, of course, I have listed some of the contributions of Newton to mathematics, but I don't know whether I'm really competent to explain these things. I only read this things, what is his contribution to mathematics. Newton's interest in mathematics began in 1663 when he brought an astrology book at a fair in Cambridge and found that he could not understand mathematics. Unable to understand trigonometry, he studied geometry. Newton and Leibniz independently developed calculus, both integral and differential calculus. Newton is generally credited with generalized binomial theorem for any exponent. And contribution to the theory of finite differences was the first to use fractional indices to employ coordinate geometry to derive solutions to Diophantine equations. Coordinate geometry was invented by Descartes. You know that also. And then Newton, of course, approximated the partial sums of the harmonic series of logarithms. And this slide I have added only for the sake of continuity. And also Newton was the first to use the power series with confidence. And then, as I told you earlier, in my talk, first I have covered about the early life of Newton, and then his contribution to the law of gravitation, laws of motion, and also the optics. And now I'm giving you some details about the positions that he held in the government during his life. Newton was the warden of the Royal Mint in 1696. He was, of course, these are all very prestigious positions that Newton held during his lifetime. He was a member of the Parliament of England from 1689 to 1690 and also in 1701, representing the Cambridge University. As a Master of Mint in 1717, his reforms added considerably to the wealth and stability of England, which earned him knighthood from Queen Anne in 1705. And of course, he received many honors and many awards and all that. He was Newton undoubtedly a very great physicist of the 17th century, who lived, I told you, later part of 17th and early part of 18th century. And he stands in comparison with Einstein, and both of them, they stand on the same pedestal. And he received many honors. And to mention a few here, he was a Lucasian professor, a very prestigious position in 1669. Fellow of the Royal Society, he was elected Fellow of the Royal Society in 1672 for his invention of the reflecting telescope. He was the president of the Royal Society from 1703 to 1727, member of the Parliament of England from 1689 to 1692, and also in 71. He was the warden of the Royal Mint in 1696, Master of Mint in 1717, and of course he was knight. I mean, he received his knighthood from Queen Anne in 1705. And I want to say a few things about his religious views also. Although these laws of motion and universal gravitation, also the laws of motion and universal gravitation become the best known discoveries. He warned against using them to view the universe as a mission, because those days, the church was very powerful. And you know how Galileo suffered and all that. I don't have to elaborate on those things. Galileo suffered a lot because he believed in Copernicus' theory about the planetary system and all that. And Newton said gravity explains the motions of planets, but it cannot explain who set the planets in motion. So he believed that gravity explains the motions of planets, but it cannot explain who set the planets in motion. And he also said that God governs all things and knows all that is or can be done. Newton saw God as a master creator whose existence could not be denied in the face of grandeur of all creations. And this was his religious, views, and in support of the church, so that he was probably a very highly diplomatic person. And then I would like to give one or two quotes about what others have said on Newton. French mathematician Lagrange often said that Newton was a great genius who ever lived, and once added that he was the most fortunate, for we cannot find more than once a system of world to establish. In fact, those days, things were in the nascent stage, and whatever you invented, it was a great invention. That is why I am reminded of a book written by George Gamow titled 30 Years That Took Physics. See, you know that when this quantum theory was invented by Max Planck in 1900. And quantum physics, Max Planck, of course, is called father of quantum mechanics or quantum physics. And from 1900, quantum physics started, and the foundations of classical physics were shaken. Because the relativity came and it questioned, that Newton's laws are not valid at great speeds, particularly at speeds very close to the speed of light. And then the atomic structure was invented. Then Compton, but so many developments took place on basis of the quantum theory. So the foundations of classical physics were shaken to a certain extent. Not that they were, totally wrong, but Newton's laws, that they had limitations. Earlier, we did not know about the limitations of Newton's laws, but after 1900, with the discovery of quantum physics, people understood the limitations of classical mechanics. So from 1900 to 1930, many developments took place. And that's why George Gamow has written a book titled 30 Years That Shook Physics, where, he elaborates on all these developments that took place between 1900 and 1930. And it is said, during this period, everything was new. So even a third-rate scientist could do a first-rate work. But now, the developments, so many developments have taken place, and the developments are so advanced and all that. People say that now it's very difficult even for a first-rate scientist to invent a third-rate, work. To invent a third-rate work. But those days, Newton, of course, was an authority, and that's why Lagrange said he was very fortunate, for we cannot find more than once a system of world to establish, because Newton had already established Newton's law of gravitation and the laws of motion and the universe, how the planets, the planetary system and things like how they work and all that. And English poet Alexander Pope was moved by Newton's accomplishments, and he wrote the famous epitaph: nature and nature's laws lay hid in night. God said, let Newton be, and all was light. And lastly, I conclude with a quote by Newton: I do not know what this is, of course, a very famous quote by Newton. I do not know what I may appear to the world, but to myself, I seem to have been only like a boy playing on the seashore, diverting myself in now and then, finding a smoother pebble or a prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me. Thank you for this wonderful opportunity. I thank the organization and particularly Mr. Srinath for having given this opportunity to share my views on Newton, gravitation, and optics. Thank you. And also, of course, as I told you, in fact, this kind of situation should not have arisen because I'm giving a talk in as a tribute to my good friend, Dr. G. Venkatesh, who is not with us. And I feel very sorry for this, the very unfortunate, I say, occasion. But anyway, as I said earlier, death is not in our hands. And the destiny, he was probably destined to leave this world. And I once again express my condolences to the family of Dr. G. Venkatesh. Thank you, everyone.
Supriya?
Thank you, sir. Open for questions and discussions. If anybody wants to talk with sir, you can interact. I am unmuting all. So you can unmute and talk with Srikantan, sir. Any questions?
Supriya, shall I? Hello?
Hello?
Sir, can you hear me, sir?
Yeah, I can hear you.
Sir, thank you. It is a perfect fitting tribute to Professor GV, and you have elaborately explained the contribution of a great scientist of physics. Thank you for that. And if Professor would have attended this talk, would have really loved and enjoyed it. Hopefully, he also is enjoying. That's what we believe it. Sir, you mentioned about the theories rejected. The theories conceptualized by the Newton and rejected. One of the example you have given. This did happen in his lifetime or a post lifetime? If so, what
No,
was
it is
the
a
Newton?
post lifetime because this Huygens wave theory, as you know, the 1726, Newton passed away, right?
Yeah.
Okay, this Huygens wave theory was in the 19th century, and Young conducted the experiment in 1807. 1807. So it is a post-Newton period. Post-Newton period.
No, just to I mean, if any readings
Yeah,
are there,
Newton was not aware of that. Yes.
Newton was
Yes,
not aware.
post-Newton. Yeah.
Any theory during his lifetime got rejected, and what was his reaction? Anywhere recorded? Any such things are there? Because he was in a very high position in London. Generally, a scientist of that caliber, when his theories are rejected during his lifetime, reactions anywhere recorded or any such stories?
No, I have not come across anything like that. Yeah.
Okay.
Because people at that time, he was an authority, and people had told that they had no courage to contradict his ideas at that time.
Yes. Thank you.
Girish, sir.
Thank you, sir. Thank you very much. It's a perfect eulogy for Professor GV. So they're like the fight between Newton and others. So GV sir never had any fight, and you actually brought out all the whatever Newton has brought to the universe and how entire universe evolved because of Newton. So one question I just wonder. So many people say that Newton, just by observing fall of apple on his head, couldn't have actually predicted Newton's laws. He might have actually made a conjecture that okay, gravitation
It was actually
attracts everything.
People say that Newton, he got the laws by induction process. Actually, yeah.
No,
Whereas
that I
Galileo,
understand. But the number.
for example, Galileo got the laws of motion, like V equal to U plus AT equations and all that. That he conducted experiments on an inclined plane and all that. This most of that deduce on induction things like that. And later on, he, for example, you say we always talk that, he observed this apple falling on that. And then he got the idea that why the apple is falling, why it's not going up and things like that. Then he thought maybe there is an attraction. And that's how he got an idea and then worked on that.
No, I understand that. So, but that allows you to only attraction. It can simply say that we have magnet and iron attracts. But the values, whatever he has given, that wouldn't have been possible just by observing that. So, any comments on that?
No, he did. For example, he already had that Kepler's laws with him, right? At that time, he had already had Kepler's laws with him. So he deduced this law of gravitation from Kepler's laws of planetary motion. Because Kepler's law, he got that idea, and then Kepler had already come out with the laws of planetary motion, and he took the advantage of that, and then came out with he deduced the law of gravitation mathematically using Kepler's laws of planetary motion.
Okay, thank you, sir.
Questions? Shantala. Okay. If any questions,
Madam, need not be questions.
you can unmute.
Need not be questions.
Yes, sir.
Anybody can express their views and comments. Let it open. If not, questions alone.
Okay, sir. If anybody,
Raghavendra sir wants to speak.
sir, 1 minute, sir. I'll. You can unmute and you can talk, sir.
Yeah, thank you. First of all, sir, it was a very excellent presentation. And I think only a friend could have spoken about GV, as you said. Yeah, we have still not come out of all this. But the presentation-wise, I think it is a wonderful explanation of Newtonian gravity as well as optics. And incidentally, now that you mentioned it, in the first KPA newsletter, I had written a simple article on the derivation of this Newton's law, how Newton arrived at it, exactly as you mentioned. So in the YouTube chat, I've given the link to our KPA newsletter. Those who are interested can go to the YouTube link and see in the chat. Sir, it was very nice listening to you. And this debate between the corpuscular theory and wave theory, I think every student of physics should read to know how even great people sometimes can make, can be wrong. Because Newton was held in great awe, like Newton held mele adake eradne maat illa anta. But even sometimes what happens, and also the life history of Thomas Young, when he actually does that double slit experiment. Even that is very, very, very fascinating. And Newton had a very, very dominating personality. If you read his autobiography, extremely dominating personality. Yeah, but then such a wide contribution in mathematics, and always the maths department, we used to argue that Newton was the one who discovered calculus, and they would say Leibniz.
So once again,
great.
Yes, sir. So once again, see, Srinath asked. Now I'm remembering that Srinath asked, was there any argument which Newton could not explain during his lifetime? Probably the perihelion, the precision of Mercury's orbit. Well, the deviation he could not explain on the basis of the Newton's theory. Yes. Where, after it was explained only after the Einstein's, theory of gravitation. I mean, isn't it? So that is probably, Srinath, I think that's one of the things where, Newton could not explain. The perihelion precision of Mercury's orbit.
And ironically, the Newton's rings, the so-called Newton's rings, was discovered by him. But being a propounder of the corpuscular theory, you can't explain Newton's rings with the corpuscular theory.
That's
you
correct.
need to have a wave theory. So but that's another instance where
use that Newton's rings to to construct a reflecting telescope.
Yes,
to,
yes, yes.
To see that the optics of that was made. He could improve the optics of his telescope.
Yes.
That Newton's ring. That is another important.
Very true. Very true. But the explanation of the ring system itself needs a wave theory. But he was a very strong believer in
about interference. he didn't have that interference,
Yes.
because a corpuscular could not explain the interference.
Explain that.
Yeah. And in fact, as he was, this corpuscular theory was actually held in high esteem till the Huygens wave theory came, and then Fresnel's explanation of diffraction, and then Arago's experiment, and then finally it was discarded. Till then, people, of course, some people believed in Newton's theory and some people believed in Huygens theory. Yeah, that there were two groups. In fact, I was told that professionally there was a lot of arguments between the two groups, and this French Academy of Sciences wanted to settle that issue once and for all, and that's why Arago took that bold step of inviting papers from both the groups, and then he personally verified this Arago's. It's very famously known as Arago's spot. You know that Arago's spot.
Yes.
So anyway,
Fascinating.
Yes. Thank you very much for all your comments. And I hope, of course, I know I have not done any work in gravitation. It's only what I have learned from books and whatever I have learned from my graduate studies and all that. I have mentioned it here. Of course, from my teaching, I have used my experience in teaching also, because I have taught these things under graduate level, particularly the derivation of Newton's law of gravitation, starting from Kepler's laws of planetary motion. All that was there in the syllabus. So I have taught all these things to the students, and I've used this knowledge and experience to present this paper. And so as course, as you know, I am not an expert in gravitation, but I have made attempts to present whatever I know about this gravitation, optics, and Newton's contribution. Thank you very much for all of you, and I thank Srinath, also the creative organization, for this excellent opportunity. But only one thing is, I am not, of course, very happy with the occasion. That's all. That's the only thing which bothers me.
Can I make a comment, please?
Yeah, please,
Hello?
sir. Please, sir.
Sir, my name is Dr. Giridhar. I am Dr. G. Venkatesh's son.
Okay, tell me.
Yeah, thanks for that wonderful lecture, sir. I wanted to share a few things here.
Yeah, tell me.
My father, Dr. Venkatesh, always used to appreciate two books, and he always used to mention those to me, to us at home. One is that biography of Sir Isaac Newton by Richard Westphal. It is titled Never at Rest. And then the other one is about Principia. It is titled Principia for the Common Reader by Subramanian Chandrasekhar.
Yes.
So, of course, I tried to read the latter. It is very difficult and not for a common reader, of course. But one thing that my father told me struck me very profoundly. At the time of Newton, almost two and a half centuries before Einstein, the amount of background knowledge that was existing at that era, during that era, was very, very little, and Newton had to make all the discoveries by himself. Whereas Einstein had he had the backup of a lot of research work that had already been done till that time. And that helped him. That's what he used to say. So it's both of them stand on the same
pedestal. Always started from, out of intuition only he came out with all these things. But as you said, for example, Einstein, that way, of course, he was also a genius. I told you, both of them, they stand on the same pedestal, actually. So Einstein, for example, you take Einstein, he gave the explanation for photoelectric effect. The photoelectric effect, results of which were already there. And Max Planck's theory was already there, because, Planck had given already to explain the black body radiation. He had already proposed the quantum hypothesis. He used that idea. Of course, he modified it to explain the photoelectric effect. That also requires, of course, the intellectual issue. Was also an intellectual, and also to see very important three important discoveries of Einstein. One is, of course, explanation of the photoelectric effect, for which he got Nobel Prize. And the second one is the Brownian motion, explanation of the Brownian motion. And then, of course, the theory of relativity, both special and general theory of relativity. So that way, of course, both of them, of course, very genius. They were very genius. But Newton, of course, as you said, at that time, with the minimum this thing and all that, he did that work. In fact, as I told you, when he was after completion of his graduation, the University of Cambridge was closed for 18 months. And during those 18 months, he worked out most of the things. He came out with this calculus and things like that, even the gravitation, he thought about all that. And good thing that he did not listen to his mother, because his mother wanted him to be a farmer. But Newton, refused to be a farmer. He came out. And so we are all benefited. The physicists have been physics, the field of science has benefited by the Newton's, even he refused to become a farmer. Yes. Yeah.
Thank you.
I think I thank you one and all, I think.
Yes, sir.
Yeah.
Okay. We are at the end of the session. Gratitude to Dr. B.S. Shrikanta sir for enlightening us on Newton's gravitation contributions and life achievements in today's creative session. Your insight deepened us our understanding of scientific brilliance. As we are express our thanks, we also honor the memory of Professor G. Venkatesh, whose passion for science inspires. To our engaged audience, thank you for active participation. Let's carry forward this spirit of discovery and knowledge in future sessions, celebrating the legacy of intellectual giants like Newtons. Thank you, Abhiram sir, for joining us. And thank you, one and all, Satyendra sir, Jaljakshi, Raghavendra sir, so many who are related to. Yes, sir. Yes, sir.
Sir, namaste, sir.
Namaskara.
Sir, namaste. After 36 years, sir, ನಿಮ್ಮ ಪಾಠವನ್ನ ಕೇಳುವ ಒಂದು ಅವಕಾಶ ಕೊಟ್ಟರು ಸರ್ ನಿಮ್ಗೆ.
Thank you for joining. Thank you for joining.
Thanks to Srinath and the creative team.
Thank you for joining.
Remember, sir, ನೀವು ಮತ್ತೆ ಡಾಕ್ಟರ್ ಜಿ ವಿ ಅವರು ಸರ್ ಸ್ಟೇಜ್ ಮೇಲೆ ನಿಂತು ಆ ಪಾಠ ಮಾಡೋ ಸ್ಟೈಲ್ ಬಹುಶಃ ಇವ್ರು ಯಾರು ನೋಡಲಿಕ್ಕಿಲ್ಲ, ಅದನ್ನ ನೋಡಿದ್ರೆ ನಾವೇ ಪುಣ್ಯವಂತರು ಸರ್ ಆ ಸ್ಟೈಲ್ ನ.
I want to share one more thing about Satyendra. In fact, every day he is on WhatsApp, he sends the famous, the sloka, Guru Brahma, Guru Vishnu, Guru Deva Maheshwara. Every day he sends to me on WhatsApp. That shows,
ನಿಮ್ಮ ಆಶೀರ್ವಾದ ತಗೊಂಡೆ ಕೆಲಸ ಸ್ಟಾರ್ಟ್ ಮಾಡೋ ಸರ್.
Thank you, Satyendra. Thank you.
Thank you, sir. Thank you, sir.
Thank you, one and all. We are